Okay, so what we're going to be talking about today is the way that you can use the word count data that we've been collecting from a variety of different kinds of sources, and not just look at what most common words are, not just filter out to find the first word of the first paragraph, sort of toy examples that we've been doing in different problem sets, but instead to take this word count data and make comparisons across different types of documents to say, if I have a set of articles produced by Boston Celtics fans have been and Los Angeles Lakers fans in this bin, to use an example that I was just talking about with Malcolm, what are the salient differences between Celtics fans and Lakers fans? If I have 16th century sermons delivered by Protestants and Catholics, what are the differences that are salient between those two groups? And this is something that we're going to be exploring with word counts, but these are really fundamental aspects of counting and comparing things that occur in groups that we can actually apply not just to word counts, but to any kind of data that occurs of things counted in bins. When we get to talking about geographic exploration next week, we're going to look at the ways that we can use these same techniques to say what distinguishes the sorts of archaeological remains that have been found in different areas of the Roman empires. These are general exploratory tools that can also help you to make arguments about differences between different groups. And one of the reasons that we emphasize this in this class is that that aspect of comparing two different groups to each other is one of the sort of fundamental things that I think defines the sorts of arguments that people tend to make in the humanities. So we're going to start off here by looking at the chapter in the online text that is devoted to comparing and searching bags of words documents. And what this lays out are three different metrics for comparing books to each other. As I say in here, there are a lot of different metrics that you already know what they are that we've been using on grouped sets of data. We've been taking the means of groups to see what the average element is. We've been taking the maximum to see what the largest element of the group and what the smallest element of the group is. We've been doing things like sorting and arranging. All of those are transformations that you can apply within a document structure, but they're things that make sense when applied to all sorts of other elements too. And they're things that really require just elementary school math to understand. When you get into doing comparisons, that aspect starts to break down because you can't say, I want to know what word occurs more often in this corpus than it occurs in this corpus, because in almost every case, that's just going to be the, of, or and. As we looked at when we looked at word counts earlier, it turns out that there just aren't enough uses of less frequent words to swamp that really common stuff. And you can do things like stop word removal. There are tactics to get individual words out, but serious work that looks at word frequencies and at other kinds of frequencies needs to use some metrics which are a little bit more difficult to get your head around than just means and medians and sums. And what we're going to talk about today, and what I want you to be thinking about how to apply in the rest of this class, are three that bear a really intimate connection to each other. The first is something called TF-IDF. The second is something called pointwise neutral information. And the third is something called Dunning log likelihood. And although these are related to each other, they each give you different kinds of information. They're useful in different aspects. And so one of the things that you should think about is which one you want to use in an individual case. The first one we're going to talk about is TF-IDF, not because it's the most important or fundamental, but it's because it's the one that you have probably used the most in your day-to-day work as a researcher in the humanities. And that's because TF-IDF is the underlying technology behind most search engines built between about 1980 1980 and 2005 and continues to play an important role in a lot of search engines built in the more modern era of corporate search engines where we don't necessarily even know what's going on inside of Google. You use search engines all the time. One of the things that we can start to do is think about how to build your own search engine. And this is not something that's necessarily going to be useful in your individual research projects because you can just toss something into a search engine. But knowing what underlies it is a fundamental skill that I think everybody working in the humanities should have some more than completely trivial knowledge of. The way that a search engine works is deeply foundational for the way that we practice research. So here's our first code block for understanding what TF-IDF does and how you can use it to both do comparisons and to engage in search. We're going to load the 3 libraries that we've been working with for textual analysis. First, Julia Selje's and David Robinson's tidytext package, the humanities data analysis package from this course, and the tidyverse package from Hadley Wickham and the team at RStudio that undergirds all of our work in this class. And then we're going to do a couple of things to our collection of State of the Union addresses. First, we're going to load in all of the State of the Union addresses, tokenized using tidytext. And then we're going to do something new in them, which is to add chunks, to break them into contiguous chunks of about 200 words, or sorry, about 2,000 words apiece. And the reason we do that is that these State of the Union addresses are vastly different lengths. And one of the shortcomings of TF-IDF is that it works better when documents are about the same length. So what we're going to be doing here is looking at not just the 200 State of the Union addresses that have been given, the 230 State of the Union addresses that have been given in American history, but at individual smaller chunks of them to look for portions of text that match individual areas of discussion. This is the code that loads all of those in. As with all of these, it's good to take a moment to inspect them. Again, I'm going to highlight this and hit Control Enter, that might be Command Enter depending on your platform, to see what kind of data we are looking at here. And this starts with George Washington in 1790 saying, "I embrace with great satisfaction the opportunity which now," then we have 1.8 million more words of State of the Union addresses going on. We have all of our data about speeches. And we have this new field here, which is the chunk number of an individual address. Once we get far enough in here, we'll get into the second chunk, although it takes 2,000 words to do that. So we can't necessarily see it right away. The thing that we're then going to do is take that, group by these chunks, and count the number of times each word appears in each State of the Union address. This is a simple group by and count function. We also use a new function here called ngroups, which just serves to count how many groups there are in our State of the Union corpus, which is something that we're going to need to know for the next step. And it turns out that we now have 1,023 documents instead of just the 220. It means that the typical State of the Union address must be about 10,000 words long. The first chunk of George Washington's 1790 address uses the word "a" 21 times. It uses a lot of words just a single time. And you can see these are sort of sorted in alphabetical order in the interior here. That already gets us into 1791. So let's see if I can find something else from 1790. So yeah, in the, I guess the 1790 speech is only 2,000 words long, but "the" appears 96 times. That's probably the most common word in Washington's speech. Now we're going to do something that is different. We're going to group by documents and words, and we're going to count for each word 2 things. First, how many documents it appears in, and second, how many times it appears. And then we're going to create a new column called document share, which shows the share of all documents that that word shows up in, and a new one that shows word share, which is the share of all words it shows up in. And then this is an unnecessary thing that I'll show in the next line. So now we have a data set that says the word the appears 154,000 times in this corpus, and it appears in all 1,023 documents. The word of appears almost as many times, but there is one chunk in which the word of does not appear. Word the is about 8% of all words, of is 5% of all words, to is 3.4% of all words. This is a distribution that, as we saw earlier, follows Zipf's law of logarithmic frequency. So what I'm going to do now is show you a chart of the frequencies that compare this number here, the document share, to the word share. Oh, I need to load this ggwithal package to make that work. If we do this, you see that this is yet another plot where things are highly clustered in just particular areas. The word the appears so much more than anything else that it is all clustered in one particular end. So as with all data, as with so much data, it is necessary to do a log transformation. So I'm uncommenting these two lines up here to add a Y scale and an X scale, which transform these into a log space. And then you get a sort of interesting looking pattern. The more common a word is, the more documents it appears in, but some words appear in just a few documents. And if you assume that every word was evenly distributed in the documents that it appears in, all words would fall along this red line right here. But words are not evenly distributed in the documents that they appear in. If you say the word Iraq once in a 2,000 word chunk, it is much more likely that you're going to say the word Iraq again. If you say the word Soviet once in a 2,000 word chunk, it is much more likely that you will say the word Soviet again. There are some words that don't follow that pattern. If you say the word becoming at one point in a State of the Union address, and you here is a president of the United States, which I don't believe anyone in this class is, say that word becoming once, you are not more likely to say becoming again. Becoming almost falls along this red line here, which means that becoming is not a word that in its clustering seems to show a large sense of topicality. It is not a word that indicates what a paragraph is about. And this is something that's really important for search engines. Some words are more intrinsically clustery than other words. And that is actually a clue to how important they are for telling you what a document is about. Soviet and Iraq are two words that really actually show you more strongly the nature of a text than the word becoming. And so if you're building a search engine, or if you're asking for words that characterize a particular document, Soviet and Iraq are going to be more useful words for you to use. And this is the core intuition behind TF-IDF, is that it uses this percentage of document scale and this level of total occurrences to build scores for each individual word. Here we're plotting on a log scale. TF-IDF, the core innovation, which the inventor, I'm blanking on her name, Margaret Henkel, I believe is her name. She recently got one of those New York Times obituaries for people who were neglected in their time, an information scientist in the 1970s who came up with this concept of using TF-IDF as an information retrieval technique. The statistic that she invented is called inverse document share, or inverse document frequency. That's why it says IDF. We can change that right now. This plot says that V is at the top, right? If you look up here, if you were to use this y-axis as your measure of how much a word tells you about a book, this plot would say that V is the most important. In fact, V is the least important because V appears in everything. So what IDF tries to do, underweight words towards the top. It flips this upside down. That's what makes it an inverse. The second thing that it does is, because these log transformations are so fundamental, it actually builds that into the statistic. Which is the log of the total documents divided by the number of documents, rather than saying documents divided by the total documents, which is what we have here. If we plot inverse document frequency, you'll see that it looks basically the same. It is the same chart, it's the same words. We've got a line pointing to America right here, and you can see America in the same spot right down here in the next chart. But by virtue of taking this logarithm, it has given us a number which you can use as a weight. And when you make a search in TF-IDF space, what it does is it takes the term frequency. It says the word "the" appeared 0.5% of the time in this particular document. And rather than weight purely by that, it multiplies it against this inverse document frequency score. And because the nature of logarithms is that the logarithm of 1 is the number 0, that means that words that appear in almost all documents have their weights incredibly reduced. The word "the" gets multiplied by 0. The word "of" gets multiplied by something like 0.01, while something like Soviet or Iraq is going to get multiplied by 3, 4, 5. So what it is essentially saying is that some words are more important than other words for determining what a document is about, and that importance is based on how rare the words are, first of all, which is essentially this line from left to right here, but also critically how clustered those words are. So if a word appears like 10 times less often, but is the word "becoming" and evenly distributed as opposed to the word "Soviet," which is really highly clustered, Soviet will still get a boost in its IDF score. Then finally, what you can do is for each individual word, multiply by that inverse document frequency statistic, the thing represented on this y-axis, the term frequency inside each individual word. And you get a new data frame that shows the relative frequency of each word. Here you see that even though the word "the" has a term frequency which is somewhat high on these dots, 1.2 times 10 to the -3 might not sound high, but you have to remember that these are frequency counts that need to be multiplied against the total amount of occurrences. But we can also take this and look at it in the reverse direction, see what words have the highest according to this TF-IDF metric. And those are words that appear rarely, but potentially more than once in a document. So words like gerrymander appears only a single time in State of the Union addresses. So if you were to do a search for gerrymander, it would be a really strong sign that that's a word that you really want to know about. It might make sense to actually limit these a little bit. And I'm now actually looking at this and seeing that this is not the correct calculation here. We should not be grouping by word. We should be grouping by chunk. And so we get things like expenditure is especially characteristic in this chunk of the 1802 State of the Union address. I think some of these are probably capturing especially short speeches, but these are things that show up at high rates, but that are also not as frequently occurring in speeches in general. So this function to do the transformation is something that's fundamental enough that I'm not going to you programming yourself all of the time. I built it as a function to summarize TF-IDF into the broader corpus. I want to show you what this looks like as a search engine that you can build yourself on any set of texts. You could say, I want to look for the words Iraq, Iraqis, and America. And take this TF-IDF frame that we've generated already, and ask for the documents which most strongly emphasize those terms in them. And when you ask for that, and here you see there's a filter that reduces to chunks that are over 1,500 words, which is important because we don't want to just be looking at the little tail end chunks, which are like 200 words long. I said that's important. Actually, it's not important. It's a middling detail. And then a join against this thing here filters frame. If we look at it here, this is a frame that includes all of these words. When we join to our search terms, that will reduce it down to solely the words that are in this frame, because that's what the join is. It finds only the words that are limited here. You can think of a join as another way of doing a filter if you have a data set that you're interested in. Then we find the sum for each chunk of the TF-IDF scores for that word count, and we can say what are the individual chunks that show up the highest in this particular search term. And the answer that we get here is something which should be reassuring if you know when we've talked about Iraq and American State of the Union addresses. It's the second chunk of the 2008 State of the Union addresses. It's the third chunk of the 2008 State of the Union address. The first of the 2004 is a series of State of the Union addresses during the period of the Iraq War. So even though the word America is something that shows up at an immense rate in searches, if we were to ask for when people talk about America on its own, we start to get 1996 Union addresses and other things intruding in here. When you ask for filters down to just things that include the more distinguishing, the rarer words that you're looking at. We can also use this to actually start to read things, the first 50 words of each of these 2,000 word chunks that match these queries. Something about the Iraqi elections in this chunk from 2008. He's still talking about stem cells in the 2004 one, but he will get to Iraq at some point in the future. Something you can do with TF-IDF, and that is frequently done in the digital humanities, is something that Ramsey does in his the book that we didn't read in this iteration of the class that he wrote about digital humanities work, is to use TF-IDF to ask what are the distinguishing words that represent any set of documents. So for example, we can take our State of the Union addresses and treat the level of document not as these individual chunks that we were looking at above, but treat the entire corpus as spoken by one president as a document. This is where Whitmore's level of address is a really useful thing to think about. We might want to think about 2,000 word chunks, but we also might want to think about much larger bodies of text, which for Ronald Reagan is 8 years of State of the Union addresses. For FDR is 14 years of State of the Union addresses. Those larger chunks are useful if what we want to be comparing is presidents, as opposed to comparing individual shorter documents that we want to look for. And this is, again, I want to emphasize, one of the major areas of potential for creativity and potential for innovation in the way that you design a research question, is what the documents that you create are. I'm asking about presidents. That's not an especially original way of thinking about things, but there are all sorts of interesting ways that you could think about this. One thing you could do with the State of the Union addresses, for example, when people have this, is to look at the difference between election year State of the Union addresses and off-year State of the Union addresses to see the way that the diction used shifts when there is a pressing matter of something being elected. But we're going to do something relatively simple here. We're going to group by the president, count how many times words appear, and then use this summarized TF-IDF function, which does all of that work of adding logarithms and creating the full frequencies, and creates a new column for us called .tf-IDF. And the reason there's a dot in front of it is that it's sanitary, let's say. Sometimes when you're using special names inside of functions, to preface them with a dot in case somebody already has another column that has the same name. let me show you what this looks like. Whoops, I deleted it, undo. I'm gonna highlight, and again, this is that thing that you should be doing. If you have not been doing this, start doing it just to get it under your fingers and try to remember to keep doing it because it will make things easier, even if it seems harder at first. Highlight up to the end of this thing and hit Control Enter to run it. And this is going to give us for each president the most strongly distinguishing words. Barack Obama, it's the word that's. And the reason for that is that nobody in the text of their State of the Union addresses has the contraction that's before Obama, or a few people do, but not at anywhere near the rate that Obama does. Donald Trump's most characterizing word is applause. That's actually a corpus creation issue, which is that I have used the UCSC collection of American presidency texts for the pre-2016 State of the Union addresses. But since then, I've just been pulling it from the whitehouse.gov website, and the whitehouse.gov transcripts have applause built into these speeches. And this is one of the things that this kind of exploration often lets you do, is understand important distinguishing elements of your corpus. If you want to work with textual data, you will be able to use these to find errors in it conceivably. Harry Truman is defined by 1947 because he was president in 1947 and he talked about it a lot. Some of them are less characteristic of, are less, what am I trying to say? Some of them are more real distinguishing. Donald Trump actually does say tonight more often than anybody else does, or at a more distinguished rate than anyone else does. George W. Bush talks a lot about Iraq, and Jimmy Carter talks a lot about the Soviet Union. George Bush also says tonight, and this is an interesting feature here. People, just because a word is distinguishing of one president, because we have so many here, it can be distinguishing of multiple different presidents. And in fact, one of the reasons that tonight shows up for a number of these people is that, there it is for LBJ as well, is that State of the Union addresses only became evening televised appointment watching in, I believe, the Johnson administration. And before that, delivered in the daytime, as most work in the United States is transacted. So the word tonight is a distinguishing word for many of the post-1960 presidents compared to each other. If we were to do a filter here and say, I only want to know distinguishing words looking at addresses that happened after the year 1965, we would actually get a different set of words distinguishing people, because many of these people may say the word tonight, and we get different sets of contractions. Some of them, that's for Barack Obama, still remains up top. Iraq is still distinguished for H.W. Bush. But the way that different words are characteristic depends on the broader that you're comparing to. And you think about what the relevant set of comparisons that you want to engage in is. We already talked a little bit about what this has to do with as a search engine. Interesting, I'm getting a different result here. Why did that change? Doesn't really matter, these are decent. Oh, I see here, and then this is the, we're restricting here to only words that have a letter in them, and taking the most common word, the most highly ranked word for each individual president. So we're just looking at these now in alphabetical order. The most highly distinguishing word for Abraham Lincoln is emancipation. Andrew Jackson is chambers. Calvin Coolidge is marketing. These are actual, these are things that are not trivially informative about the agendas of these speeches. We could also do something like add another column to this and get a different set of results in which we look not at the distinguishing words for each president, but distinguishing words for each speech. And so Abraham Lincoln has two speeches in which emancipation is his most frequently distinguishing word by TF-IDF, but one which is high, which is invalid. And this is one of the powerful things about working in a coding language like ours, that you can just shift your level of address. You can change the documents that you're working with, but perform the same analysis, that there is a distinction between the analysis that you are doing and the corpus that you're doing it on. And once you've figured out what is a useful way to explore something, you can easily change the area that you're looking at it in by simply adding in new terms. So TF-IDF is a sort of document retrieval technique. I want to talk about two other metrics descend not from information retrieval and library science, which is where TF-IDF comes from, but more for the world of information science. These are things that are mathy, that date more back to sort of Claude Shannon and Bell Labs in the 1950s and the 1960s. These are things which are not thought of as purely textual elements. TF-IDF is something you can use on other types of documents, on other types of collections of information, but it does have the notion of a document baked in so heavily into it that it probably makes less sense to use if you're thinking about geographical distributions or if you're thinking about the counts of people in the census. I think people often underestimate how easy it is to apply document techniques to other kinds of data. That's something we'll explore more with geography, but it is definitely worthwhile to think about what are techniques that have been built and are universally used in aspects which are different than just text retrieval. Point-wise mutual information is a really fancy pants word. I myself was intimidated by PMI for years because it sounds like such a complicated concept. But what it actually means is something really simple. It is the ratio of how much you would expect something to happen versus how often it actually does happen. And so let's dig into this again by looking at the way it works on the State of the Union addresses. This is, again, basically the same data that we've been working at, how much time each president uses each individual word. This line of code up here looks at these and tries to estimate if Barack Obama used the word of at the same rate as every other president, if George W. Bush used the word back at the same rate as every other president, how often would he use it? And the reason that you can't simply say what is the average of all presidents is a really simple one. It's that George W. Bush has fewer words than Bill Clinton does. So it is not enough to simply say he should have used it the same number of times as Bill Clinton. You have to multiply by the number of words that he used. But this is not a especially complicated set of calculations. First, we just calculate how many times, how many words there are total in this entire corpus, how many words are in all of the State of the Union addresses, look at how often each word appears overall, and then group by each president and say, how many times does each president use this word? And those are two different statistics. One is how often is the word used overall? How often does the president use it? Both expressed as frequencies of all the words in those texts. And then you have a thing which is the ratio. How often does this person use it compared to how often does everyone use it? So if George Bush uses it twice as often relatively as other presidents, that number will be 2. If he uses it 10 times as often, that number will be 10. If he uses it half as often, that number will be 0.5. If he never uses it, it would be 0, although the nature of the joins here means that we don't have to see the zeros in this text. So let's look at this data and see it for just a particular set of words. Say, I will make America great. I'm going to say it again. So a sentence that I don't know if Donald Trump has actually said in the State of the Union address, but you can have thought about writing at some point. That failed here. Object PMI score is not found because we never ran this line up here. So Barack Obama used the word again 38 times. A word share significantly less than he used the word America. These numbers are so small that it's hard to read them, but essentially what's happening is that this number divided by this number tells you relatively how often they use them. Barack Obama uses the word America just slightly less than the other presidents in this area. He uses the word make about 20% more often. Donald Trump, in fact, does use the word great at a huge rate compared to other presidents. 80% more often, almost twice as often uses the word great. The word I for both of these guys is less than it is for the typical president since 1980. This is often a trope of political commentary and State of the Union addresses, that whatever president you don't like talks about themselves more often than other people. In both of the two most recent presidents have actually used the word I less. Have used something like we more. We could scroll through these 36 things, but it is often better to just plot them and look at them directly. So here you see for each of these people, whether they use it more or less, the 100% line is somewhere right about here. So make is more frequent for Clinton and Obama, is much, much less frequent for Trump than for anybody else, and is a little bit under for Reagan and the Bushes. And this is interesting here, that's sort of like a political divide. Bush and Clinton say I much more than W, Reagan, Trump, Obama. Great is indeed Donald Trump's personal word. There are huge differences in the usage of America, although George W. Bush uses it more than other people. And again, is a super Reagan distinguishing word. Perhaps because he also had Make America Great Again as a slogan at some point. So we're plotting an axis on this scale here, but this is another case in which it actually makes more sense to cast these things logarithmically. Because if you think about the numbers that we're using here, the way that it makes sense to talk about this is Bill Clinton says make 10 times more often than the typical president, or Bill Clinton says make half as often as the typical president, or sorry, 1/10 as often as the typical president. If you were to do that in a linear space, those would be the numbers 10 and 0.1, but really the midpoint here is 1. The midpoint here is, do you use it more or less? And if you use it half as often, if you go down from 1 to 0.5, that is the same as going from 1 to 2. So again, it makes sense to engage in a logarithmic transformation. And that is what the formal definition of pointwise mutual information is. It's simply this ratio of observed over expected with a log transform added to it. We can add that log transform right here. I'm blanking on how to do it. When you forget something, there it is, trans. You can just use your tab completion to find it. I decided to say transformation, but in fact the argument is just trans. You get 100% nicely oriented in the middle, and only the outliers stick out here. It becomes much more clear just how firmly these things are clustered around 1.0. And you can also see more clearly the outliers of who uses things less than other people. Both Clinton and Obama say great much less than the 4 Republican presidents in this corpus. But I'm going to remove that for the next version of this book. PMI is something that is adequate to do for any kind of set. We looked a little bit a while ago at skin colors in the Cruise data set. Pointwise mutual information is a really sensible thing to use if you want to, say, compare skin color and hair color to each other and say, where do you get skin colors intersecting with hair colors at a rate different than you would think about. I use a couple different functions in this that might make sense in some individual things. I expose them to you here, but if you want to find out exactly what they do, the way to handle that is to put it into your search engine over here in the help bar. Oops, that's not the search engine. Complete. Complete. Completed data frame with missing combinations of data. So this here is saying, I want to add a bunch of zeros for skin hair combinations that do not exist. And I use something called add count, which adds in the counts for skin without doing a whole bunch of groups and regrouping like we did above. And then we create these same expected scores. And the same way of creating a ratio of observed over expected, with one exception here. If something doesn't appear, a log transformation raises an error, we say, let's just pretend that things appeared once if they didn't appear at all. This is a weird fudge, but it's actually a very common fudge in working with pointwise mutual information, because when you're talking probabilistically, what you're trying to say is, you know, Bill Clinton doesn't say the word Iraq in his State of the Union address in 1994, say. Imagine if Bill Clinton had spoken for 20 hours instead of like the 2 or 3 hours that Bill Clinton's State of the Union addresses tended to go on for. He might have said it eventually. And so the way that you express that when you're talking probabilistically with word count data is to often fudge these things up to say, well, maybe he would have said it once. Maybe we pretend he said it one time. And this serves to temper your expectations, to make things be less extreme than they might be otherwise, and to allow you to engage in these log transforms. So let's look at what this plot looks like. This gives us a set of interaction probabilities in the New Bedford crew lists data that we've been looking at. This is on a Viridis scale. I think we might want to do scale, color, gradient, type equals divergent. Continuous. Yeah, whatever. Would rather have a scale here that actually showed us 2 different colors in 2 different directions. But you can see here the yellows are the more strongly positive things, the things that appear more than you would expect based on the overall ratio. So some of the most over-appearing combinations are white hair and mulatto skin, white hair and bee skin, whatever bee means. Sandy hair and sandy skin appear very strongly together. And some combinations appear much more rarely than you would expect. Curly hair and light skin are rarely appearing together. Brown hair and Indian skin appear rarely together. Brown hair and black skin almost never appear together. And then this one really gaping hole here is that woolly hair and light skin are almost completely incongruous, which is just a way of sort of confirming that what woolly hair means tends to be people of probably African or Austronesian descent. You can also use something like this to start to understand what's being seen that you might not have known about before. We can look at the way that yellow skin might be associated with different types of hair to see what does it mean to say that somebody has yellow skin. And the strongest, the yellowest elements here show you that yellow skin is associated with black hair, with curly hair, with woolly hair, with white hair. So yellow as a skin color here seems to be associated with a set of hair colors that probably indicate that yellow skin is actually being used as a way to describe those same people of African or Austronesian descent, as opposed to being used as something to describe, as in sort of contemporary American racial vocabulary, the way that people talk about I see that you've come on here. I'm just going to wrap this up quickly. The way that people talk about Asian descended people as having yellow skin, that seems to not be an especially live category, although maybe there's some of it with black skin. And it's certainly not being used to describe people with brown or light hair, which you might expect, because in fact, like the people with yellowish tinges, I mean, and I don't know, maybe I just see things racially differently than the way that everybody else does. But I would guess that the people with the yellowish tinges in their skin tend to, in general, have lighter hair as opposed to darker hair, which is what's being indicated. One last thing that you can do with pointwise mutual information is to think about documents not just in terms of individual words, but combinations that occur together. We can use the same add count function to look at the bigrams that show up in a collection of texts and see what pairs of words show up more strongly together. So the pointwise mutual information for the word set followed by per is extraordinarily high because these two words occur as a pair. Supreme Court occurs as a pair. June 30th, which is the end of the fiscal year, occurs as a pair. And this sort of starts to get into some of the stuff that Shore is talking about. What are the larger constructions that people work with that are not just words? Something that you could look into, which I think would be interesting, is the way that different kinds of combinations of words appear over time. That new groupings of pairs of words emerge together. Words become more closely associated with each other as time goes on, or words become less closely associated with each other as time goes on. It'll give you a sense about the evolution of the discourse. So that's for mutual information. I'm going to stop this now to talk to Olga one-on-one. And I'm going to give another brief explanation of Dunning-Love likelihood, which is a statistical transformation, in just a little bit.